Okay, welcome everybody. So in this video, we are going to revisit this idea of what an inner product is on Rn that we've already discussed. And let's talk about how we can extend inner products more generally onto other vector spaces. So for example, vector spaces of polynomials or functions or matrices. How can we extend these ideas into more general vector spaces? And so the first question might be, well, why would we want to do this? And recall that inner products are really nice because they give us a way of measuring lengths of vectors. They give us a way of measuring distance between vectors. They give us a way of measuring angles between vectors, how to determine whether two vectors are orthogonal. And we've seen that it is really convenient when working with Rn to set up orthonormal bases in some situations because that is going to simplify quite a bit of calculations. So I'd like to take a look at how we can extend this concept of inner products that give us ways of measuring distances and angles to any general vector space V, not just vector spaces that are R2 or R3 or Rn, but vector spaces that might have vectors which are things like polynomials or functions. Okay, so let's define what an inner product is on a vector space more generally. So this is going to be a function that assigns to each pair of vectors u and v inside this vector space. And so again, we do not know what u and v might be. So they might not actually be column vectors, but they could be polynomials or matrices. So we're going to denote the inner product of these two vectors sitting between these angled braces. So this angled brace, u, v angled brace, means the inner product of the two vectors u and v. And so as long as this function, which takes as input two vectors from the vector space v and is going to assign them a real number, is going to be what we call an inner product as long as it satisfies the following axioms, where we're going to let u, v, and w denote arbitrary vectors in our vector space V, and c is denoting some arbitrary scalar. So these properties that I'm about to show are going to need to hold for all such vectors u, v, w, and scalars c. So the first property is a commutative property. That is, if I take the inner product of u and v, that is the same thing as taking the inner product of v with u. Behind door number 2, we have associative type of property. And so this second property is saying I can first take vectors u and w, add them together, and then take the inner product with v. And that needs to be the same as if I first took the inner product of u and v and w and v separately and then added that together. The third property is dealing with multiplication by a scalar. So if I take the inner product of c times vector u with vector v, that's the same thing as taking scalar c times the inner product of u and v. The fourth and final property tells us that if I take the inner product of u with itself, we're going to connect this back to, this is going to tell us something about the length of vector u. So we're going to want these values to be greater than or equal to 0. We're not going to want to have negative lengths. And in fact, we're going to say that u inner product with itself is going to equal 0 if and only if u is the 0 vector in vector space V. So whatever that might mean for vector space V. So we really want the magnitude of only one vector to equal 0, and that would be the 0 vector. So we've got these 4 properties that we need to be satisfied in any vector space that we can equip some function that takes 2 vectors as the input and outputs some real number. If that function satisfies these 4 properties for all such vectors u, v, and w and scalars c, then this vector space, moreover, is called an inner product space. So to be an inner product space, you first of all need to be a vector space And then secondly, you need to have this additional function that satisfies a certain number of properties. And now you've got even more structure with an inner product space. We now have a whole geometry that we've mapped on top of this vector space in the sense that we can measure distances and angles in our vector space. So the vector space that we've already considered, Rn, that just consists of column vectors of n entries, with the usual dot product that we've discussed that we showed on the previous slide, that is an example of an inner product space. And I want to take a look at some examples of other inner products, first of all, that we can put on Rn that may or may not satisfy these properties. And then we're going to generalize these results to vector spaces of polynomials and functions.